Jason, can you use your mic?
Hello, good morning. Sorry, I'm eating my breakfast right now. So
Okay, no, that's good. Thank you. Thank you. Have a good breakfast. I wish I was having my breakfast. All right. Okay. Right, midterm. So we're gonna pick the questions this week. I think she posted it, but it will be 2.2, 2.7. I mean, okay, everything up to 4.6 is the last topic, and everything we did in between. I don't remember. Like section wise. Okay. Oh yeah, what did you, yeah. Can you like tell me the? Okay, let me go to Slack and look at the topics, and I'll be back. Just a second. Let's see. So let me write it down. 2.7, then 4.1, 4.2, 4.3, 4.5, 4.6. Okay. Okay, so let me write this again. So the topics are 2.2, 2.7. All right, again. 4.1 to 4.3, 4.5, and 4.6. What was 5? Right, yeah, yeah. So, okay, let me add the caveat. All this material, but for F, R, and C. Yeah. The book only, yeah, the book only does RN. We do everything. Original fields, yeah. Okay. Yeah, if you have a question about this midterm, just let me. I'll pick questions from the bus. So if you have a suggestion, you can tell me. Okay, inner product. This will also be in it. I don't remember what number it is, but it's there. So inner product. Why do we study this? So you've studied dot product, and it's the same. We wish we have dot product. We don't. But the closest thing is called inner product. And we will have similar things, and I will go through them one by one, like Pythagorean theorem. like angle, length. So I will go through them, but this is the object that is the closest to dot product. Okay, and it says that when you take an inner product with yourself, you're non-negative, you're almost linear in each slot, and when you swap, you pick up a conjugate. Because these guys could be complex. If it's real, you just call symmetric. All right, good. So yeah, of course, the most interesting example is the dot product that came first. But if you go in other places, you will also see this. Namely, so let me write this, A, B, or whatever. So X and Y are in Rn, R2. And this is called a quadratic form. So let me prove you a positive definite, which I failed miserably last time. So we have xy 1, 1, 0, 2, and then xy. I will prove that this is non-negative. But yeah, I mean, let's do it. So if you do the calculation, you get x squared xy plus 2y squared, and yeah, anyhow, and then you use what is called the complete the square formula. Okay, so if you use this formula, you can rewrite it like this: x plus y over 2 squared, and then 2y squared, whatever, it's 3/4. 2 minus 1/4 y squared. This is what? 4, 8, 7/4. Yeah. So this is the sum of two positive numbers. So it's non-negative. And if you set it to 0, what do you get? You get x plus y over 2 is 0, and y is 0. So you get x equal y equals 0, which is what you want. This is called positive definite. You're 0 with yourself only when you're the 0 vector. Yes. Yeah, I mean, but yes, that's right. This is transpose. So you go like this. So the first guy here, you go like this, and it gives you x plus y, and then you take dot product. Yeah, if you want to think about it that way. Yes. Yeah, I have different xy here. I know, like, because I didn't like to use ABs because I have B here. Yeah, let me write something else. Let me call it AB, and AB are in R2. Oh yeah, this is transpose. This will be transpose. Yeah. Yeah, otherwise you can't even multiply. Yeah, that's why we. Correct. But this is very general, in fact. So you take any matrix with positive eigenvalues, and you look at the same. Yeah, so you look at this inner product. This is called a quadratic form, and it has all the conditions. So same thing. X x of A is 0 if and only if x is 0. And this shows up all over the place. So in statistics, this is called covariance matrix. So this is a major object. Right, so let me explain, let me at least show you the positive definite. So next week, we can approve the spectral theorem, which says that if your matrix is symmetric, so this means Aij is equal to Aji, okay, you can look at this, and it has positive eigenvalues, lambda I is non-negative, and it has to be strictly positive, okay. Then you can decompose A into this form. Okay, so this is more than just diagonalizing. This is not of the form A Q inverse DQ. This is of the form Q transpose DQ, where Q transpose is equal to its own. Where Q transpose is equal to inverse. So who cares about these matrices? It turns out you can classify them. They're just like rotations and reflections. So they're not that many. That's the whole point of this. That you can easily get to diagonal matrices just by using a very known objects. Anyhow, in our world here, I will use this to show positive definite. So let me do that. Right, so X transpose A X. I set this to 0. I want to get that X is 0. Okay, let's do that. So you plug in the spectral theorem stuff like this. Okay. Transpose flips the objects. So you can write this as Q X transpose diagonal QX. And you call this guy Y. So you write Y transpose dy. Okay? All right. And this guy is 0. And we're going to show that X is 0. Right. But this diagonal with positive eigenvalues. So D is of the form lambda 1, lambda n, with lambda I strictly positive. And suppose y is equal to y1 to yn. Can somebody tell me what is d of y? Just to see if you follow. Yes. Okay, thank you. And then if you further multiply by y transpose, this is just dot product. So you get lambda 1 y1 squared all the way to dot product. So lambda 1 y1 squared all the way to lambda n y1 squared. And if you set this to 0, because your eigenvalues are all strictly positive, that's why you need strict positive, you get that y1, y2, they're all equal to 0. We're not done yet. So that shows that y is 0, which means that qx is 0. And q is invertible. So, and remember, invertible, when you are in the same space, is the same as injective. Okay, when you go same space to same space, you have injectivity. So you have x is q inverse of 0, q is a linear map, so x is 0. Okay. Yeah, I mean, if you take any applied course that has linear algebra, this is like one of the topics. I mean, they won't prove spectral theorem. We will do this. They will just use it. Right. If you have a question from the chat, just use your mic. Okay? Just use mic. All right. Let's go. Another inner product that you will see in the book is called the trace inner product. This is for matrices. It's mostly used in physics. From what I've seen. So you take two matrices and you transpose one of them, and you take this product. So let me prove you positive definite, just to give you some intuition. So I will prove to you that if trace of A transpose A is 0, then A is the 0 matrix. Right. So trace, just to remind you, right? Trace is sum of diagonal entries, right? Is that okay? Sum of diagonal entries. But A transpose A, in general, if you look at the diagonal, what is that? This is AIK, and let me call it BKI. Or I don't like this notation. Just call this B and call this A. I don't like that. Just use A transpose. But this is transpose, so flips. So you get squared. Okay? I'm not done with it, I'm just saying, like, we'll just play with matrices now. And, all right, okay? So that's step one. And the trace of A transpose A will just be summation over I of this, of these guys. So you get a double sum. Can you tell me, if I set this to 0, why am I done? That A is in fact the 0 matrix. Yes, I know it's obvious, yeah. Yeah, all the elements are there, there's nothing missing. Because K goes over 1 to n, and I goes from 1 to n. And they're all squared. And if you set a sum of squares to be 0, they're all 0. So AKI is 0 for all KI 1 to n. Okay. Okay. Yeah, I'm just doing the harder one. Linearity, you can show it. It's not hard. Okay, so this is the perfect inner product for matrices. And it's basically the dot product because, like you see, we got this double sum, just like dotting the entire rows. Another one that you will see in the book and in Axler all over the place. Even in finance, if you go to finance, this is called the L2 in your product. And you're basically integrating functions. And from 0 to 1. So I know this very well. Let me talk a little bit about positive definite. So f of f is equal to 0, 1 f square of x. So again, this is sum of positive, so it's no negative. Again, you should think about this as the continuum dot product, because this is really, if you approximate 0, 1, this is roughly summation of xi, gxi, 1 over n. the Riemann integral. Anyways, the point is this is like dot product for these two vectors. So this is like f dotted with g. So we're always coming back to dot product. We haven't gone too far. That makes sense. Okay. And of course, we will not prove this. You can just use it. That if this guy is 0 and continuous, you get that f is 0. Okay. This requires epsilon delta, and you don't know what that is. Unless you have a better argument. If you think of a good argument, just tell me. Do you do? Yeah, it has to be at every point. That's the problem. This interval is like almost everywhere, but you have to prove it at every x. Yeah, you have to approximate. Yeah, okay. I'm so sorry. I'm sorry. I brought by. It's over again. Alfonso. Okay, I miss Alfonso. All right. Here's another linear product for every vector space. Okay, here's the standard choice. So you give me any vector space in some basis B, then remember the coordinate map takes you from V to R of dimension of V. And yeah, you just define it as the dot product of the image. So now you have an inner product for any vector space you can imagine, because we built this for every V. So we just have for everybody. You don't get construction for free. Okay. All right. Okay, inner product. Why do we care about this? So here are some things. First, we can define length. It's called the norm. So you just take the square root of the inner product. And then what's my question? Yeah, why are we allowed to take square root of inner? I know it's obvious, but I just want to say, yeah, because this guy is positive. It's a non-negative, so you can square root it. Yeah, in complex numbers. Yeah, but we want length. Yeah, that's right. Right. So the Euclidean dot product is just the Euclidean distance from high school, right? So you have like, yeah, this was the Euclidean distance, right? So remember, you computed like you used Pythagorean theorem, all this stuff, square root theorem. So this is the Euclidean distance. And of course, the L2, that's how quantum mechanics is built. Yes, so LP, I mean, I don't know where you saw it, but I'm very happy you did. It's 1 over P 01 F to the P. And you can do it for every. That's right, yeah. And so here's my friend had an interview in finance, and they asked him which of the LPs is a Hilbert space, meaning that you can define an inner product, and the answer is L2. So this guy is a norm, but it does not come from an inner product. You cannot write FG of and get this. You can only do this for L2. So he will get you a job. If you get a job with this, like me. All right. So Yeah, why is it a length? Well, first of all, if it has zero norm, it's the zero element. Let me sketch this. So this was square root of VV, and you square both sides. And by positive definite, this was just the condition. The only time your dot product with yourself to be zero is when you're on the zero guy. So it has a notion of zero length. It has a notion of being scaled. So if you scale your vector, you scale the norm. So again, that's what you expect from your length to do. If something gets larger, its norm should also get larger. Okay, I know this is obvious, but it took us like hundreds of years to do it. And what am I doing here? Oh, I'm proving it. Sure. Right, so yeah, so I have to prove this, it's a result. Right, so we start from the left, and we have lambda v, lambda v. You have linearity in the first, so that's obvious. But unfortunately, in the second component, because we work with complex numbers, we have lambda bar. Okay, can someone tell me what lambda bar is equal to? Yeah, so this is generally for complex numbers that they you get the modules. Okay. Yeah, so this is lambda square BV, and you take square roots. Right. Okay. So yeah, when you do your proofs, remember that you only have conjugate linear in the second component. In this course, in the book, everything is real. So don't get mixed up. Here, we do complex, in the book, we do real. So for him, it's bilinear. For us, it's conjugate bilinear. Because you get lambda bar. Don't get lambda. So don't get confused with the book. Okay, we have length, now we want to have an angle. Let me just write so you've seen this, right? Yeah, okay, good. So the dot product has the following formula. You give me two vectors, x with angle theta, and y with angle phi. And so their difference is theta minus phi. And when you dot them, you can extract this angle from here. Okay. And I'm even proving it for you. So when x and y are in R2, you can represent them along the circle. Okay. Right. They fall somewhere on the circle. And then you dot them. So let me dot x and y for you. So we have x cosine theta times cosine phi with a y plus x sine theta times sine phi with a y. You take out x and y's. And then you use the trig summation formula. And this trig summation is equal to this difference. So this is a trig identity. Yeah. Good. If you have a question, just tell me. So this is cool and it works in Rn. In fact, if you want to define angle in Rn, you just write the following. You define it as x dot y over their arms. That's how you define angle in higher dimensions. Two vectors, but I have a proof with, I'm not going to do it now. The point is any two vectors span a hyperplane always. There's a plane that they span, so you can define an angle there if you want a geometrical. In like during like R to the 100, two vectors always span an R2 plane. There's a way to like, and then in there you have an angle. Because generally, what the hell is the angle? Okay, good. Because I don't like this definition. I like the way of building it. But if you look online, that's how you define it. All right. So unfortunately, there's no angle for general spaces, but we have the closest thing to it, orthogonality. So we say two vectors in like abstract spaces are orthogonal when the inner product is 0. So question, when x and y is 0, what's the picture geometry? How can you show that? I'll do it. So when the in between angle is 0, what does that tell you about theta minus 5? Yeah, it will be a multiple of pi over 2 plus 2 pi k. Who cares? Pi over 2, yeah. So it will just be a pi over 2 guy. So it will be perpendicular. We'll do it this way. So we managed to say this. So there's a notion of orthogonality for general vector spaces, right? Because if I mean, remember, we're working with like P2R, for example, right? Like minus 6 plus 4, stuff like that, right? What the hell is an angle of two polynomials? But I will do this, yeah. All right. And maybe you've seen this, a vector is called normal to a subspace if when you dot with every other vector, you get 0, right? This is more than geometry. All right. Now I'll just roll through these theorems because we're not going to test them. I'm just going to show you they exist. So Pythagorean theorem said the following, that if you want to get on a right angle triangle, so this would be u plus v. This is u, and this is v. So you did this in high school, hopefully. The summation of these two gives you the hypotenuse, and this carries through to all dimensions, all vector spaces. What else? Cauchy-Schwarz, you will say this in physics a lot of the times. You have this bound for the inner product. So remember, x, y was x, y cosine theta minus phi, right? So if you take absolute values and you use that cosine is less than 1, you get the same thing for dot product. Like all these things come from Rn. That's how we find them. Just to show you like what's going on back. So we know these formulas and we're like, oh, I want this to be true. Yeah, it is. Yeah, trust me, it's like luck. It's not like we're just guessing. All right, and then we have triangle inequality. So this, yeah, this is for general triangles. Right? Okay, fine. So you don't have to know this, just to see that a lot of things carry through. All right, now let's do some interesting stuff. So why we look at orthogonal is because we want orthogonal bases. And the rest of the 2 weeks, we will spend it on these guys. So if it doesn't make sense, please let me know, because we will keep coming back to this. So let me do a silly example. Take B to be 1, 0 and 0, 1. So this is E1, E2. And then if you dot them, so use the dot product. You get 1 times 0 plus 0 times 1, which is 0. So your standard basis is orthogonal. But not every basis is. So for example, take, oh, okay, can you tell me an example of a basis in R2 that's not orthogonal? Yes. Yeah, perfect. And you have, yeah, you have 1 times 1 and 1 times 0. So even though you have a basis, it's not necessarily orthogonal. So it's quite an achievement if you can get one, and we will, using what is called Gram-Schmidt. So you did this in 2 to 3 for Rn. We will do it for all vector spaces. And yeah, orthonormal, when you dot with yourself, you get 1. So 1, 0, 1, 0 is 1 times 1. This 1. Okay, what else? Okay, I see. I did the examples already. If you give me an orthogonal basis, I can make it orthonormal. This is a table. I divide by the norms. Okay, that's all. So you don't have to think about orthonormal from now on. This is very easy to get. The hard part is getting orthogonality. So forget orthonormal, orthogonal. If we ask you for orthonormal, just go orthogonal, and then at the very end, just divide. Okay, good. Why do we care about these? So one very powerful result is the following. We spent the last month telling you that vector spaces have bases, and you can express every element as a linear combination of the bases. But how do you find the coefficients in practice? You don't know. You have to do it by hand, right? You have to like sit down and like remind you. Remember we had some crazy stuff like 1 minus plus x, x squared. This is a basis for P. Let me put on 1 here. So this is a basis for P2R. And then I ask you to represent, x. Okay, this is kind of easy. Like, you get the point. Like, the basis could be very complicated, and you have to sit down and compare, and it's not systematic. Okay, this is systematic. So here you just compute. You compute the projection onto the basis. That's really why we study inner products, because you can do this. It's the main reason. To make a Yeah. Otherwise, yeah. It's not. I mean, it could like you're gonna have view on both sides. Yeah. Exactly. Just a second. Let me do an example because I don't want people to get lost on this. So take V to be 1, 1, and remember when we wrote these things like 1 times 1, 0, and 1 times. Let me put a 2 here. 2, 0, 1. This is just a projection. So you're dotting 1, 2 with 1, 0, and you're multiplying and you're dividing by the norm of 1, 0. Plus you're dotting 1, 2 with 0, 1. And you're multiplying by 0, 1. That's how you get this. So this guy, this complicated expression is 1. And this complicated guy over here is 2. No, no. Huh? Oh, I see. Let me see this. No, but still, like, I mean, you know the components, but you don't know how to express it as, like the example I said here, right? You have X, and you need to write it in terms of these guys. So you will sit and go like 1 plus 1 times 1 minus plus 7. Well, here you will get this. I mean, this example is stupid. You could have many of them, and it could be a mess. Yeah, you will just compute the projections. So, I mean, I have to give you an inner product. Right? I don't have to rush for. Yes, that's right. You have to. Yeah, there's a lot of stuff here. We'll go in detail, but that's right. And I will be able to give you these coefficients. Is that okay with everybody? Okay. But yeah, that's the whole point of this inner product. Because before we had no idea what AK is, now we have a systematic way to find it. All right, let's prove this. Right, B is a basis. We spent the last month to show that B exists a basis, and so you have an expression for B. And CK here we take it to be any field. Yeah, it's fine. Let me just do what I also propose. Okay. Okay, this is easy. So you saw this. Nothing in here. Now you take inner product of both sides. So both sides. So both sides. And if you do that, you get this. Can someone tell me why I get this? What property of inner products we are using? No, before you go to that, just the first step. I know it's obvious. Okay, then if you know it's obvious, but what property am I using to do this? The answer is simple. I just want to know if you know. Yes. Yeah, okay, good. Thank you. So we're using a linearity. Right? Because V is a summation, and you just bring out the sum. So you bring out the sum. Okay. Then yeah, let's go to then exactly. So yeah, go ahead. So right. So this is 0 when I is not 1 by orthogonality. Okay. So this is the survivor, and you can do the same thing for any BI. Or how to finish? Wow. Okay. Okay, let me finish because it's a big jump. So you do this for every other BI. So, and you get CI, BI. Okay. How to finish from here to get the statement? I just want to see. Yeah. Yeah, go ahead. Oh, I thought you, okay. So how, yes. Yeah, yeah. So then CI is BBI, BI, which is the more squared. So that's the specific formula. You don't have to write AK anymore. You can write down the projections. Oh, I see. Right. So V is this projection, right? So V BK BK norm of BK. Can somebody tell me what's the coordinate map of this V? Even from the Zoom people, you guys can use the mic. Yeah, so there it is. Yeah, so it would be exactly. So it would be VB1, B1 squared, all the way to VBN, BN squared. Okay, so now you know your coordinate map specifically. So yeah, there's many advantages, right? Because if you remember, even finding coordinate maps was a hassle when we did this matrix representation. If you want to find the matrix representation, and you have to find gamma B, and now you just have gamma. Okay, what else? We have projection. Yeah, I mean, okay, right. So that's what I want to say. That so let's find the matrix representation. Since we asked to do a concrete example, let me do one. So what is that? This is AB dotted with square root 2 of 1 divided by, so this is a normal basis. So okay, let me just do it. 1 squared, square root 2, 1. You know what? I'll just write E1. So this is E1, E2. And then AB square root 2, 1 minus 1. All right. And I'm done. I just compute this dot product and I give you the coefficients. I don't have to like sit down and guess how to write AB. So the first guy is, so it's A plus B square root 2, E1. And then the other guy is A minus B square root 2, E2. So the AB of in B basis will be A plus B square root 2 and A minus B square root 2. You have to do change of basis. Like remember, if you want to go from like basis, the standard basis to this big math, this other matrix, this other basis, you have to compute the change of basis. So then AB in B is the change of basis starting from AB. And you have to find this and you have to compute every column. You know, there was a lot of stuff here. It wasn't that easy. But here I just compute 2 dot products and I'm done. Okay. Yeah, so orthogonality is your friend. All right. All right. So yeah, these coefficients. Yeah, so today, and I'm almost done. Tomorrow we can approve a theorem for this. So first let me define them. So yeah, when you want to project into a vector, so you have a vector u and some general vector v. This is how you define projection. Okay. So this is the projection vector. Again, this is all from Rn. And you can also do this for general subspace. So we give you some general subspace, and they ask you, find me the minimal distance to that subspace. Okay, hopefully I'm using familiar words. So you have a vector v, and this guy here inside the subspace is called the projection of v to this subspace u. And this is the general formula, and I will prove it. I will prove that this is in fact in u. And we will also prove that this is the minimal distance. It's the closest vector inside u to v. So, anyways, we'll talk. Okay, thank you. See you tomorrow.
Oh, sorry, can I ask you a question?
Yeah, yeah, sure.
About the website. They gave you a matrix, and they were like, those are like A values, and they said, oh, A values in the matrix not diagonalizable.
Right.
I'm just wondering how to like the actual question. Like, I
Well,
know the actual answer.
oh, did you ask the question on Piazza? Because I answered the guy. I told him to use the criteria. One of you?
I know the criteria in theory, but a geometric multiplicity has to be equal to other. Find the geometric multiplicity. You know, span. I need to find how many of factors like are.
Was it hard?
Well, for you. We just both run out. I guess I'm sorry, I don't answer. Wait, but my first question was, yeah, I want to get that. So I don't like that. Never miss an opportunity. Exactly. So, algebraic multiplicity, I'm assuming is this.
No,
right? Like, okay, what's the algebraic multiplicity has to be because it's like over complex.
Yeah. No, but we don't know what the. Did you compute the algorithm? Yeah. Like you find the characteristic polynomial, you find the algorithm.